Two maps that shouldn't match, but do. Take a neuron forest and a sky full of galaxies, and you'd think the resemblance stops at poetry. But line up their maps and patterns start shaking hands. Both worlds live on sparse wiring. Both prefer short paths and tight clusters. Both balance reach against cost like someone's paying the bill. Start with topology. In brains, the connectome isn't a mess of wires. It's modular clusters linked by selective highways. In the cosmos, we call them halos and clusters at the nodes, filaments for the highways and yawning voids between them. In each case, a few hubs carry a lot of traffic, while most nodes keep to modest degrees. That skewed degree distribution isn't an accident. It's what you get when growth rewards connection, but wiring is expensive. Now look at clustering. Neurons love local neighborhoods, mini networks that think together, then pass messages along to other neighborhoods. Galaxies do a similar dance. They pile into groups inside larger superstructures with filaments tying them together across surprising distances. The result is small world behavior. The average path between 2 points stays short, even when the network is huge. That's efficient. It means information, energy, or matter doesn't slog through endless steps to get where it's going. The shocker is scale. One system is measured in millimeters, the other sprawls across billions of light years. Yet when researchers compare basic network statistics, clustering coefficients, path lengths, modularity, even the shape of degree distributions, the numbers often land in comparable ranges when normalized. Studies by Franco Vazza and Alberto Felletti, for example, highlighted quantitative overlaps between the brain's connectome and the cosmic web. Not identical, comparable. Enough to raise an eyebrow, not enough to declare a revelation. So let's be honest about boundaries. Similarity doesn't mean sameness. A brain fires electrochemical spikes across synapses. The cosmic web moves gas, stars, and dark matter under gravity, kicked around by radiation and feedback. There's no central processor in the sky, no unified mind pulling levers. What we're seeing is convergent architecture. When you push a system to be efficient on a strict budget, it tends to pick the same tricks. That budget matters. Brains can't lay infinite axons. They'd overheat and run out of space. The universe can't smash all its matter into bridges. Gravity would win locally while expansion wins globally. Both systems solve the wiring cost problem by using hierarchies. Dense local clusters for heavy lifting. Long but sparse highways to keep everything within a few steps. It's a fractal-like compromise. Self-similar patterns repeating across scales, but with variation that keeps the whole thing adaptive. Energy and information flow reveal the parallel from a different angle. In cortex, spikes travel along dendrites and axons, shaped by synaptic weights that strengthen or weaken with experience. In the cosmic web, material flows along filaments into halos, while radiation, winds, and jets blow back out, sculpting the corridors. The push-pull creates feedback loops that are eerily connectome-like. Reinforce productive routes, prune the wasteful ones, keep paths short, avoid redundant, expensive sprawl. Here's what nobody expected at first. Across roughly 27 orders of magnitude in size, both networks land near similar efficiency sweet spots, short paths, high clustering, sparse global wiring. It hints at a shared rule: maximize throughput under strict constraints. Different physics, same math. The details diverge, but the blueprint rhymes. And this isn't just simulation aesthetics. Large surveys like SDSS and DAISY have directly mapped galaxy filaments and voids across billions of light years, revealing the same modular, small world geometry in the sky that the statistics predict. Still, analogy is a tool, not a conclusion. It helps us ask sharper questions. For example, if brains and the cosmic web both settle on small world layouts, what happens when you stress those layouts? In neural tissue, cut oxygen and the network narrows. Connections fail from the edges inward. In the universe, accelerate expansion and filaments stretch thinner. Distant nodes slip out of reach. Hold that thought, because this is the parameter that ties the maps together. Efficiency under sparse wiring isn't a luxury, it's a necessity, and it's fragile. The very designs that keep path lengths short also concentrate vulnerability in the long bridges. Break enough of them, and the network stops being one thing. If that's true, there's a natural next question. How did the cosmic web assemble a layout so efficient in the first place? To understand the flatline we opened with, we need the moment the cables went live, the first time this universe found a way to be connected. Birth of the cosmic network. 3 minutes after the Big Bang, the physics was simple. Hot plasma, no structure, just pressure and light. The weirdness came earlier in the last sliver of inflation, when quantum jitters were blown up to macroscopic seeds, over and under densities at 1 part in 100,000. Quiet at first. Gravity turned up the volume. As the universe cooled and expanded, overdense regions tugged a little harder and attracted more matter, deepening wells. Underdense patches bled into growing voids. In between, matter didn't fall straight in. It slid along sheets and ridges into threads. The web didn't need design, it precipitated from geometry. Around 380,000 years in, electrons and protons paired up, the fog lifted, and the cosmic microwave background streamed free. Dark matter kept gathering. Baryons, ordinary matter, needed time to cool and settle. Millions of years later, the first halos hit the right mass and density. Gas collapsed, heated, cooled by primitive chemistry, and ignited the first short-lived metal-free stars. They flooded neighborhoods with ultraviolet light, detonated and stirred gas, sometimes blowing material back into filaments. Crude plasticity. Use a path, strengthen it. Overuse it, disrupt it, then let it regrow richer. Reionization spread as bubbles of transparency around infant galaxies and black holes. Bubbles merged along filaments where galaxies sat. The network's first firing. Geometry began to carry radiative influence, regulating the gas that would feed the next generation. Feedback mattered. Supernovae and early active galactic nuclei throttled inflows, cleared choke points, and redirected streams. Too little and halos overate, too much and corridors starved. The rhythm emerged. Inhale along filaments, exhale through winds and jets, keep lanes open and distances short. The skeleton thickened. Small halos merged into larger nodes. Filaments braided and sometimes snapped and rejoined under shear. Voids grew emptier as their boundaries sharpened. New galaxies formed where pathways already existed, supply lines were destiny. Environment wrote biographies, junctions feasted, thin spurs went lean. By the end of the first billion years, telescopes and simulations agreed. Most galaxies lived near filament spines, and most stars formed where supply and pressure balanced. Physics turned tiny differences into arteries and organs. Complexity set up shop where connectivity was best. But success carried a warning. Small world networks thrive on dense local clusters plus a few long bridges. The cosmic web achieved that mix because matter was scarce and expansion kept stretching the canvas. Every bridge cost mass. Every detour cost time. Performance increasingly depended on keeping those filaments intact. Where you sat on the web decided your future. A galaxy with 2 fat pipelines could ride out a bad epoch. One with a single thin umbilical risked quenching if that link faltered. The web wrote possibility into space. And here's the hinge to the present. Building a network is one thing, keeping it stable is the real trick. Early on, gravity drove while pressure and feedback kept lanes from clogging. Later, a quieter force took the road. Expansion didn't just stretch distances, it thinned the bridges that made the universe small, world efficient. The cables went live. Now watch what starts to tax them. The network rulebook, efficiency versus cost. A living network runs on a simple trade. Keep paths short and resilient, but pay for every bridge. Brains and the cosmic web converge on the same solution. Small world layouts with high local clustering, a few long connections for reach, and minimal total wiring so the system doesn't bankrupt itself. In brains, local neighborhoods handle most computation while a handful of long-range tracks synchronize distant regions. In the cosmos, galaxy groups and clusters do the dense work, while filaments keep separate basins within a few steps. The payoff is speed. The risk is fragility. Long bridges do a lot with a little, so when they thin or misfire, regions drift toward isolation. Wiring cost sets the boundary. The brain is capped by space, energy, and heat. The universe is capped by mass. Only so much baryonic matter can be stretched into filaments after halos claim their share. Every kilogram in a bridge isn't in a star, so corridors stay slender. Voids are huge. Highways are thin. Cost forces elegance. Redundancy is selective. Too much everywhere blows the budget. Too little and single failures kill roots. The web sprinkles backups near hubs and junctions, braided filaments that split and rejoin, much like white matter tracks fan into cortical areas as bundles, not single cables. It's a hedge against local catastrophe without paying global rent. Feedback tunes throughput. Galaxies pump energy back into the web, supernovae stirring and venting, active nuclei heating halo gas and sometimes pushing along corridors. Like synaptic weights adjusting with traffic, infall rates, metallicity, and morphology shift with winds and jets. The goal isn't maximum flow, it's sustainable flow. Efficiency under sparse wiring pushes you toward modular clusters with a few long links and toward hubs that shorten paths cheaply, until hubs concentrate load and vulnerability. Brains buffer with layered modularity. The cosmic web buffers with a hierarchy of halos, group, cluster, supercluster, with multiple access roads. If a primary route starves, a secondary spur can keep a trickle alive. Budgets evolve. Gravity thickens nodes, making local paths denser and cheaper. Expansion stretches space, making long paths thinner and more expensive. Strategy shows up as structure. Redundancy stacks near nodes first. Peripheral spans remain single lane. It's triage, written in filaments. And here's the twist that sets up the fall. Small worlds don't fail uniformly, they fracture at bridges. In brains under hypoxia, long-range integration falters before local processing. In the universe under acceleration, intercluster links lose throughput while bound structures persist. Local gravity wins, global connections lose. The rulebook stays, the background changes. Enter the force that taxes every span. The antagonist arrives, dark energy's quiet coup. While the network was optimizing itself, short paths, braided spans, feedback keeping arteries open, something else was changing the background rules. In the late 1990s, two teams led by Saul Perlmutter and by Brian P. Schmidt with Adam G. Rees, looking at Type Ia supernovae, measured how fast distant galaxies recede. Everyone expected a slowdown. Gravity should be tapping the brakes. Instead, the data bent the other way. Far beacons were dimmer than a decelerating universe would allow. Space wasn't coasting, it was speeding up. That pivot gave a name to the quiet force in the ledger, dark energy. Call it vacuum energy, a cosmological constant, or an unknown field. The effect is the same. As the scale factor grows, the average matter density thins, but dark energy keeps the same pressure and energy density. The tug-of-war shifts. Gravity still binds locally, deepening wells, thickening nodes. Meanwhile, expansion stretches the baselines between those nodes at an accelerating rate. Bridges get longer even as they try to carry the same load. Independent lines of evidence agree. Planck's CMB measurements plus bow from SDSS Daisy pin down a flat lambdictum universe with dark energy dominating the recent expansion history. Here's what that looks like when you stand on a filament. Gravity is pulling you downhill toward a cluster. Gas trickles along, sometimes in sheets that roll into threads, but the roadbed space itself lengthens under your feet. At first, inflow wins, you still make progress. Then, over cosmic time, the Hubble flow ramps up between the bigger basins. Past a certain separation, the throughput across the corridor falls. Not because the pipe is sealed, but because the upstream signal, gravity's invitation, no longer outruns the widening gap. It's like two towns on a single-lane causeway as the tide rises. The road is still there. The crossings get rarer, slower, then effectively stop. Stakes move from abstract to personal for galaxies on the margins. Closer to the nodes, redundancy and depth by grace. Farther out, single-lane spurs thin. Once dark energy dominates the energy budget, roughly the last 5 billion years, the balance tilts hard. Intercluster filaments don't snap like ropes, they diet. Their density drops as the background expands. With lower density comes weaker pressure gradients and longer cooling times, so less gas condenses into stars along the route. Starvation spreads from the bridges inward. What was once a two-way supply line becomes a memory of one. You can see the fallout in simulations and surveys that track infall rates and connectivity. Cluster growth continues, but increasingly by eating what's already inside their gravitational reach. The rate at which fresh material crosses the long baselines declines. The giant component of the network, the set of nodes mutually reachable within practical travel times, starts to contract in a useful sense, even if mathematically the graph still exists. That distinction matters. On paper, a path remains. In physics, the clock kills it. Meanwhile, feedback doesn't stop. AGNs still flare, winds still push, but their influence becomes local gardening rather than regional engineering. Jets that once could stir the corridor a few megaparsecs down now mostly shovel their own yard. The same energy budgets that once helped keep lanes open can't compete with the rising toll. The network rulebook remains valid, the price schedule changed. The result is ischemia written in comoving coordinates. Tissues, filaments, starved not by blockage but by distance outpacing delivery. Microstory. Think of a lone spiral galaxy parked near the lip of a filament that feeds a modest group. Early on, it drinks. Cold gas dribbles in. Minor mergers spice its disk. New clusters of blue stars dot its arms. Over a few billion years, the stream tapers. The galaxy still shines, still rotates, but the outer reservoir that once fed it retreats past practical reach. It mines its own halo for a while, then turns to older gas recycled by dying stars. The tempo slows. Its future shrinks to what it has on hand. Impact cascades. Isolation grows first between superclusters, then between clusters, later between groups. Local gravity wins hard where it's strong, building thicker, more resilient organs. Global links lose quietly. The small world advantage narrows to neighborhoods. Average path lengths measured by travel time, not just by connectivity, stretch past meaningful. The network doesn't die, it provincializes. There's a temptation to ask for a single timestamp, the moment the coup succeeded. In reality, it's a gradient. But there is a threshold, when dark energy becomes the dominant term, after which the direction is set. Paths that might have been maintained with modest mass now demand impossible subsidy. Bridges that would have been repairable under slower expansion degrade into ceremonial spans. From that epoch on, the future belongs to bound sanctuaries and whatever they can hold together. The quiet coup finishes without fanfare. No crack, no shudder, just acceleration turning every span into a longer bet. The antagonist doesn't break the web, it pulls it thin where it matters most. And that's why the next question is whether the universe stays connected. It's how much can be saved inside the organs that refuse to let go. The stroke hypothesis, percolation and the cosmic disconnect.